Well, hello and welcome to MOS Live. I'm so excited for today's Ask a Scientist because we are joined by three scientists who work in the field of quantum technology. And they're here to help us understand exactly what that is and to answer some questions from you. Now, this is a really timely topic because just recently, the National Science Foundation, which is an organization that funds a lot of scientific research, well, they announced something called the Q12 Education Partnership, which will work to bring lessons in quantum science and technology into kindergarten through high school education. And the Museum of Science was actually a part of the initial planning of the core concepts that will be included in this new education initiative. Now, we'll find out why learning about quantum science is so important from our guest scientists in just a moment. But first, my name is Megan, and my pronouns are she, her, and I am delighted to be your moderator for this program. Now, if you're joining us on Zoom, please feel free to start entering your questions for our panelists at any time by clicking the Q&A button on your screen. And we'll do our best to get to as many of those as we possibly can in just a little bit. Now, if you'd like captions, you can access those by clicking the closed caption button at the bottom of your screen and selecting Show Subtitles. And if you're joining us on YouTube or Facebook, unfortunately, we can't see your questions at this time, but we're thrilled that you're tuning in. All right, let's get started. I would like to invite our guest scientists to go ahead and turn on their cameras and microphones and introduce themselves.
Hey, everybody. Glad you guys could join us today. I was just going to introduce myself with a quick story as to how I got here. So I grew up always interested in how things work. I would take apart small gadgets to look inside and frequently try to put them back together, but usually in a way that wouldn't always work the same as it did when I started. I'm sure my parents loved that. But I remember spending lots of times building these simple mechanical devices from Legos as well. And it wasn't really until college when I started to learn just about how wacky the universe really is. And my fascination with how these little gadgets worked evolved into a fascination with how fundamental physics worked. And instead of using Legos to build cool gadgets, I get to use atoms and light itself to build these cool quantum machines that hopefully we'll be able to talk a little bit more about.
Great. So my name is Sarah Moradian. I'm a postdoc at UC Berkeley out here in California. Maybe slightly differently to Michael, I didn't really know what I wanted to do for a long time. I actually bounced around when I was a kid. I loved reading. I wanted to be a journalist for a long time. Then I went to MIT. I studied biology. I studied computer science, and then finally landed on quantum information science. And Michael's right, it's a lot like Legos, but with atoms instead of little blocks. So I trap single calcium ions. You can see some behind me. And then I shoot lasers at them to see what happens and try to build exciting things out of them.
Hi, my name is Eric Burson. I'm a PhD student at MIT. And I, similarly to Sarah, I guess I bounced around a little bit when I was making my way to this field. And actually, I originally started off in biology, and I was always very interested in imaging, things like MRIs, CAT scans, stuff like that. And as I was going through my education, I found out that there are ways to use quantum mechanics to actually improve these types of medical imaging things. And I thought that was super exciting, so I started working in that field. And it turns out, the more I worked on it, I found out that these quantum systems have all these crazy types of applications. And so from there, I got more interested in this area that I work in now, which is something called quantum networking, which is basically trying to make a version of the internet that operates on the principles of quantum mechanics. So yeah, maybe we'll talk about that at some point as we get further on. But basically, I use lasers like these things back here to send quantum particles over long distances around the Boston area and MIT.
Great. Well, thank you so much for those introductions. We are so excited to have you here. Now, before we get to our questions from the audience, I'd like to start out with some basics to get the ball rolling. So now we're talking about quantum science and technology today, which is based on the scientific theories of quantum physics or quantum mechanics. So what do we mean by quantum physics? What is that?
I could take an initial stab. So when we say classical physics, we mean describing the way things work in the world that we live in. So if I throw a ball at you, where does that ball go? Quantum mechanics is the study of things at the atomic scale. So how individual atoms interact with each other, how light interacts with each other on the nanoscale. So smaller than you can see. I don't know if either of you have clarifications.
I can add one quick thought. So another big difference between the classical world that you're used to and this crazy quantum world that we study is that fundamentally in quantum mechanics, the reason it's called quantum to begin with is that you're used to everything just being continuous. If I move my hand across the screen, it happens continuously. But in our world of quantum that we study, actually everything is quantized. So it's all discrete in nature. And thus we get our quantum mechanics field.
Yeah, I don't really have much to add. I think that about covers it. Yeah.
Great, well, thank you for that. So you are all working down at the scale of teeny tiny atoms and particles, stuff that is way too small for us to see. And this world of quantum physics is often referred to as strange or even spooky. So, what is it about it that makes it like that? Is it really that weird? How does it get that reputation?
Yeah, I guess that there are a couple properties kind of related to some of the things that Michael alluded to about how when you get to things that are very, very small, the physics that describes them just behaves, it looks different than what we view in sort of the everyday macroscopic big world. And I think that that's one thing that is sometimes hard to sort of comprehend. And it's actually, quantum mechanics describes everything we see. It's just that, so this discretized thing that Michael explained, how like everything is moving in small steps. And everything is sort of in little chunks. If I take a big step back, all those little tiny steps can look like one continuous motion, for example, like taking this example of my hand moving across the screen. So it's counterintuitive to think about what's happening on this small scale, even though it is the same thing that's happening at the large scale. So I think for some people, that can be a little bit of a step to understanding how that sort of quantum to classical transition kind of works. But there are a couple other properties that are somewhat spooky as well, if you guys maybe want to talk about those.
Yeah, so entanglement is a big word that we use a lot in quantum science. And so that's just the idea that two particles, even if they're super far apart, if you've entangled them, they share some information. And so if I measure one, I know something about the state of the other. And that is something that doesn't really happen in classical physics. And I think maybe why people say that quantum is spooky or scary or confusing is also because our intuition doesn't work on those scales. Like it's really easy to have an intuition about what happens in the real world. Again, if I throw a ball at you or if I knock my water bottle off the table, what's going to happen. But in the quantum world, we don't live in that world. So we don't really have an intuition of how it works.
At the end of the day, we're all scientists. You're making observations of the world around you constantly just so you can operate in this world. And it is just that you don't interact with the world at a quantum scale. So that is what sets it apart and makes it weird and different and unintuitive.
Great, thank you. So maybe the quantum world is not so weird, it's just different and we're not used to it. So we've got a lot to learn here and I'm excited to kind of dig in some more into these topics in quantum physics and quantum technology. But now, quantum physics as a field kind of began, over 100 years ago, where we had all these initial discoveries into atoms and particles and what they can teach us about nature. And that was kind of considered the first quantum revolution. But now a lot of people say we're in a second quantum revolution. So what's so revolutionary about what's happening in your field right now?
Maybe
go for it, Sarah.
Maybe it goes back to what Michael said about the Legos. So initially we were studying quantum physics and just studying to see how things work, but now we can actually start building systems at the quantum scale. So we can put together a chain of ions like this and have them control their interactions. So it's a step forward from just observing to controlling.
Definitely. And I think a lot of that is built on other technologies and other areas that developed. You know, if you'll read sort of scientific papers from decades and decades ago, people will say, oh, if only we had this thing that we could do, we would be able to make this amazing thing using quantum mechanics, but they didn't have it. And now with the development of things like lasers like this, or like the technology behind Michael is this very fancy refrigerator, and all of the sort of things that go into building that, we now finally have those things that let us finally realize kind of the applications of all the things that people wrote about 100 years ago.
Great. So that's really exciting. So now in this first quantum revolution, you know, we discovered things about atoms and particles, and now it sounds like you're actually able to use those atoms and particles to create new types of technology, which is super cool. Now, before we move on to our audience questions, I would love to hear from all of you a little bit about what excites you the most about what you do. Maybe what are some of the most exciting applications of quantum physics that are coming out right now, or just personally, what makes you want to do what you do?
I can go ahead and start with this one again. So, I mean, it's a bunch of different worlds, at least for me, joining together. I mean, I am very interested in the science behind quantum mechanics. So being able to work and learn and think about new concepts using the rules that we've learned from quantum mechanics is fascinating to me. But at the same time, I also am super excited about what quantum information through quantum networking, through quantum computing, what that's going to enable in the future. And so I love being able to be part of the community of scientists and engineers to work on building something quantum.
Maybe for me, it's slightly different. I think there are a lot of cool applications of quantum, definitely. I think for me, though, what is exciting is just playing with these new systems, seeing what happens. A lot of these systems are actually quite simple in some ways. So you can really think about what should happen, do an experiment, and then the best feeling is always seeing that the experiment matches what you expect. Or even sometimes it's better when it doesn't match what you expect, and then you have to think a little bit harder and figure out why. I come from an engineering angle. So I have all my degrees in electrical engineering, not physics. And I think like the technologies that we've built and that we still need to build to enable some of this, I think are really exciting, and have a lot of interesting challenges for the future.
Yeah, for me, I guess that latter point is the thing that I find really exciting. So I'm still a PhD student, which means I'm still very much in the process of learning and, you know, trying all these different things and building up sort of my base of knowledge. And so what that means for me working in this field, we combine things from physics, we combine things from electrical engineering, computer science, mechanical engineering, chemistry. And so every day that I go to work, I have a new problem that I have to think about, and I get to learn about a new area and sort of try to become just a mini expert on one individual topic, just so I can solve one piece of that puzzle. So it's never boring because there's always something new. And I think that's one of the really cool things about this area, especially right now, is that there are people sort of across all areas of disciplines that are able to get involved in this exciting technology.
Wonderful. Yeah, lots and lots to be excited about in this whole realm of quantum physics and quantum technology. All right, well, thank you so much. And I see that we have a lot of questions coming in from our audience. So let's get to those. And now remember, if you're joining us on Zoom, you can feel free to keep asking those questions as we're talking about them right now. We're going to try to get to as many as we can starting now. All right, so you all are ready. I'm going to jump in with the first question. And we have a lot coming in. People are really curious about quantum computers and particles. So let's start off with an interesting question that goes back to kind of why people sometimes consider the world of quantum physics to be a little bit weird. And one of those sometimes weird things is superposition. And so one of our audience members is wondering about how you can use superposition, and maybe you can define what superposition is quickly. How can we use superposition if we can't measure it?
I can start off by defining it and then give you guys the hard part.
Sure.
So superposition is one of those fundamentally like bizarre things with quantum mechanics. So the two fundamentally bizarre things, superposition and entanglement. And so superposition is the idea that you can have, let's say, an electron for sake of argument, or atom, that is simultaneously in two different states. And what I mean by states here, again, is that quantum mechanics is quantized. So I can have these discrete states, but the way you can imagine that, to bring it a little closer to maybe intuition, is that if I have an atom, it can be physically in two different places at once. And it's not that I don't know where it is, it's that it actually is in both of these places. And when I start scaling that up to now lots of atoms, I can take advantage of the other bizarre thing with quantum mechanics, entanglement, which is going to now enable what we're going to want to do with a quantum computer at the end of the day, is get a reasonable answer out when there's this this notion of something being in two places, and how do I know where it is? How do I measure where it is? But now I'll give the hard part of this to one of the other two.
So I can
Maybe I can say, oh yeah, go for it, Eric.
No, you do it. No.
Okay, I'll say something and then you can, I'll say that the person who asked the question actually hit upon a very important point about superposition, is that when you measure this, so you have this electron that's in, two places at once, so it has some probability of being over here and it's a little bit over there. When you measure it, you only measure it in one location at a time. And if you tried to do that many, many times, you would get out the probability distribution of its position. But you're right that every time you measure it, you only measure one position. But before you measure it, when you have one electron or when you have many electrons and they're all interacting together, the superpositions interact really as those probabilities. And so at the end, what you measure will depend on your superposition, even if you only measure one number.
And I think the kind of the key thing is that kind of what Michael said and what Sarah said combined. So when they're in this superposition, it's not that they're 50% here, 50% here. It's really in both places at once. And so it's not kind of a random state, but it's actually a very well-defined state that behaves in very well-defined ways. So when you do what Sarah said and have a bunch of things in superpositions, you know exactly how they will interact with one another. And it's not really a random process. And so your interaction is very controlled, and you know exactly what's happening. And then at the very, very end, you measure it, and then you'll get either here or here. But hopefully, if you know what you're doing, you've constructed your interactions in such a way that you expect to get either this one with 100% probability if this answer is correct in a quantum computer, or this one with 100% probability if the other thing is correct. Yeah, but the key is that it's not really random 50-50. It's in both at once, and that is a very well understood, sort of well-defined way that interacts.
Just to drive home that last point a little bit more, at the end of the day, it's up to the person writing that quantum algorithm to write a quantum algorithm that does something useful. You're absolutely right. You can generate entanglement and superposition across everything in your computer. That's not useful. At the end of the day, you need to have an algorithm that makes one particular probability of something happening spike. And hopefully that spike is somehow answering one of the questions you had going in.
Great. Okay. So we have a lot of questions about quantum computing, which superposition is going to tie into. So let's summarize all these questions. First, can you tell us what is a quantum computer? And then maybe a little bit about what you might do with a quantum computer and how they would be different from, the laptops or regular computers or even iPhones that we're all on right now.
I think we're all kind of sitting. Go ahead.
Well, I was going to say, you two have quantum computers behind you, and I don't, so I'll leave this one for you guys.
You go first, Michael. You go.
I was simply going to say, we're all sitting in front of something that can be a quantum computer.
That's true.
But so, okay, can you reiterate the questions again?
Sure. So starting with Michael, can you tell us a little bit about what a quantum computer is and how it might be useful and different compared to the computers that we're used to?
Yeah, so that's a great question. A lot of times when we say quantum computer, it's hard to like imagine what that might look like compared to a classical computer. But at the end of the day, their jobs are more or less the same. Their job is to contain some physical system that's described by some laws of physics, either classical laws of physics or quantum laws of physics, and be able to interact with it in only a way where you can manipulate those pieces of information and get them to interact with each other to perform some kind of logical operation. And at the end of the day, the difference between the quantum computer and a classical computer is that we get to play with the additional laws of physics that quantum mechanics provides, such as that superposition and entanglement that classical machines can't do, simply because they're either too warm, too big, too something that makes them classical versus quantum. I guess I'll pass it on to someone else to answer the remainder of the question.
Yeah, I can say a few things. So ideally, if we had a fully operational quantum computer, you could do everything that you could do on a classical computer as well. However, what we want to do is find applications that are specifically suited to quantum computers. So where that superposition and entanglement give us powers and give us scalings that are much better than classical computers. And there are a few problems that have been found that have that property. And hopefully also more will be found. You know, when we first started building classical computers, no one thought that we would be using them to send Facebook emojis to each other. But here we are. So we won't know. I think there'll be more and more applications as we build more and more complicated quantum computers.
Great. So what are some of those applications that are kind of specific to quantum computers that, you know, the properties like superposition and entanglement that would really help us benefit from those?
So one that I think is very exciting, just from my biology background, is something called quantum simulation. Basically, the idea is all the things that happen in our body, chemical reactions with like neurotransmitters in our brain, the way your blood cells take up oxygen, all of these chemical interactions are happening on the nanoscale, and so they're quantum mechanical things. So whenever we have a computer simulation or do calculation to try to figure out what's going on, we're always kind of making an approximation about what's actually happening. With a quantum computer, you have things that behave with the exact same laws of physics that the actual real world things do. And so you can simulate what's happening a lot more accurately. So for things like discovering new medicines, or understanding certain ways the body works, kind of on that really small intercellular level, that's a really open problem for quantum mechanics where it can really thrive.
Cool. So we have a few questions about how you actually work with stuff at the quantum scale, which sounds like it'd be really hard to do. Atoms and particles are like the smallest of things. So if you could maybe we do have one question, so maybe you can just, before you answer this question, just give us a couple of examples of what quantum particles are, and then how you actually work with these and incorporate them to be useful in quantum technology.
I can start. So I work with trapped ions. So really what we do is we have a big chunk of calcium and we just heat it up. So then we get little vapors of calcium flowing around. We have a really pure vacuum chamber. So there's really nothing in this chamber except for these little calcium particles floating around. And then we trap them in a series of electric fields with lasers. And so we're able to see just a countable number of ions. And it sounds like it would be really hard, but it's actually simpler than you think. You could, even in your garage, build a simple system that would trap a dust particle. And a dust particle is a lot bigger than an ion, but the principles are exactly the same. And so then we can trap ions. And what's nice about ions and a lot of these quantum systems that we use is they have some sort of, they emit light when we shoot lasers at them. So we can actually see these little blue dots, and that helps us know A, what we've trapped, and B, when we try to poke them with other lasers, we can measure what state they're in and how they're interacting with us. So yeah, that's what trapped ions are, at least.
Yeah, at the end of the day, it's really just coming down to how do you trap something so small, right? So another way of doing that is usually the mechanisms or the knobs that you have access to in the macroscopic world are going to enact some kind of field, like an electromagnetic field or something, either through light or a static voltage. But all in all, at the end of the day, it's creating some kind of localized field in space that's able to trap either an atom, like in Sarah's case, or in the case that I work on, we trap single electrons in a solid simply by applying a voltage. We know that electrons will typically flow to if you apply a voltage across something. So we just take advantage of that, like pretty much like a capacitor. And we load that capacitor instead of with a lot of electrons that maybe you're more used to thinking about, with just one electron. And that gives us our quantum state where we can put in quantum information.
I guess for completeness, we should mention one of the most popular systems is something called a superconducting qubit, which is very different than kind of the things that we've been talking about so far, because that's what we all work on. And for that, what they do is they basically, in the same way that people who make computer chips will have these like crazy fancy machines with like where they fabricate chips, basically the way that they work is that they take a piece of silicon or something like that and use a laser to kind of write a pattern onto the chip about where they want their qubit to be. And then through the sort of magic of fabrication, where they write that laser ends up being sort of where metal gets deposited. And so that metal will then basically form a loop that will, in a similar way to what Michael said, kind of trap some type of quantum particle inside that loop of current. And then they can talk to it by basically just like sending current to that loop or back out like you would with any electronic circuit.
Great.
Maybe
And
one more. Oh, sorry. I was going to say light is the last quantum particle that none of us have really talked about. So photons, the light that you see around us, if you could, the lasers behind Eric, for instance, you can manipulate those just with mirrors and lenses, or, your sunglasses if sometimes they're polarized, so you can see different things if you move them around. So polarization is actually a really important quantum property of light as well. So we basically use fancy polarized sunglasses to control.
Great, thank you, Sarah. So I think we have time for just about one more question. And Sarah, what you just said about photons, I think is maybe a good tie-in. Can you quickly tell us what the quantum internet is or could be?
Eric, you want to take that one?
Sure. So the quantum internet is basically, the next step of having quantum computers. So people are talking about all these things that we can do with quantum computers. And in the same way that when we first made normal classical computers, we wanted to have them start talking to each other, people want to do the same thing for quantum computers. So that's kind of, I think, the general baseline idea. It also turns out that there are just some kind of interesting things that will happen if you have quantum systems that are talking to each other despite being very far away. One very popular field of working in quantum information is called quantum key distribution. And basically what that means is, it turns out that the rules of quantum mechanics will let people share keys, basically informational decoding keys, such that they can communicate with one another with 100% security. So, I can be in Boston and Sarah can be in California, and if we share these keys, it's impossible for anyone to intercept and decrypt our communication. So that's sort of one application of it. that has also been very popular. But in general, I think the answer is just in the same way that people want to have a normal internet, we want to have a quantum internet so we can send quantum emojis and things like that.
I'm very much looking forward to what a quantum emoji will look like, and whether or not I need a special microscope to see it. That is super cool. So before we say goodbye, now that we're almost out of time, it sounds like, you know, quantum science and technology is really going to be probably a big part of our future. So do you have any sort of parting words of advice or encouragement for our young audience members who might be interested in getting into this field or studying quantum physics when they get older?
Yeah, I can go ahead and start with this again. I mean, the fundamental thing is keep asking questions. The only thing that really separates us as scientists or engineers here is that we're still asking those questions. We're asking why about everything. And with that, of course, you have to keep a healthy amount of skepticism when people answer that question. And just, you know, never just accept that that's just the way it is, because there's always a reason behind it. And having the interest in trying to figure those reasons out is really what brought us, I think, all of us, to where we are today.
Yeah, definitely stay curious, keep asking questions. And there are many different facets to quantum computing. So, you know, there are many different paths that could lead you here. So, you know, I think figuring out what you're interested in, as both Eric and I said, like I studied a billion different things. I jumped from thing to thing to thing until it stuck. And I think that was a really important part of the process because now, you know, I know that I really like this.
Yeah, stole my answers there, I guess. But yeah, like Sarah said, there are a lot of different ways to get into this field. And I think the key thing, just whatever you're interested in, if that's quantum computing, if that's quantum information, if it's not, do the things that you enjoy and, you know, study the things that interest you. You know, nowadays there are so many resources online, be they from the Museum of Science or, you know, online video series that people make, that there are a lot of different ways, or, you know, going to the library, people still do that. So many ways to get more information about the things that you're interested in. And, you know, starting where you are and then following your passions where they lead is the best way to be doing things that are interesting later on in life.
Great. Well, thank you so much. That is such a nice way to end the show. So I want to just thank all of our panelists so much for being here with us. And I'm going to invite you now to say goodbye.
Bye. Thank you, everybody, for coming.
Yeah, great seeing everyone here.
Thank you. All right, well, if you're interested in learning more about quantum science and technology, you can head over to Nano Nerds on YouTube, where we have a whole bunch of videos to explore on all sorts of different topics in quantum physics and quantum technology. And if you're interested in learning more about upcoming quantum physics education in the classroom, you can check out the key concepts for future quantum information science learners at qis-learners.research.illinois.edu. Now, there is so much more going on over at MOS Live. So check us out on social media or visit us on the web at mos.org/MOS at home to see what we're up to. And if you enjoyed this program, please consider supporting the Museum of Science by visiting us at engage.mos.org/welcome. Your support will help us provide access to science experiences online and at no cost. All right, well, thank you again for joining us. We had so much fun with you today, and we will see you next time. Bye-bye.